Today we study ESA17H, its solution of the simple harmonic oscillator 1. We consider the equation of motion for a simple harmonic oscillator. So a simple harmonic oscillator consists of mass that is attached to spring and a spring. So spring, we characterize the spring with the spring constant K and mass of the object to be m. The equation of motion is F equals ma. Force, net force is mass times acceleration, the double time derivative of the displacement x. This displacement x is measured from the equilibrium position 0. That is called the position at which the spring does not apply any force to the mass. So displacement from the equilibrium position is x. For example, if it is x, then because we consider the one-dimensional motion, we don't have to attach an arrow on top of the letter x. The force is minus kx. Here, k is a spring constant that it's assumed to be positive number. So negative value, this minus kx is a negative value. Therefore, the force, the restoring force that is called the Hooke's law, that is opposite to the displacement of the particle from the equilibrium position. We can move this one to the left-hand side. Then we have the sum of the ma, mass times acceleration, and kx should be 0. We divide both sides by the mass m to find the second order time derivative of the displacement plus some positive real number that is a k over m is a positive real number. We define this one to be omega 0 squared. We should find that this omega 0 has the dimensions of the reciprocal of time. Let's see. We find this is a double time derivative, second order time derivative, and this is omega 0 squared. Both of them apply to the displacement because the addition of the operator, second order time derivative, and omega 0 squared, they are summed. That means both of them are of the same dimensions. Here, the second order time derivative has the dimension of the same dimension of 1 over t squared because it is the time appears in the denominator. Therefore, the second order time derivative and omega 0 squared are of the same physical dimensions. Because it is defined to be k over m, we have the dimensions of time to the minus 2. Hence, the single time derivative is of the same dimensions as omega 0, that is of the same dimensions as square root k over m. Again, it is reciprocal of time. The physical standard unit of the angular frequency omega 0 is hertz, that is defined to be 1 over second. The restoring force minus kx can apply to the three-dimensional case too. But in a simple case, we can choose the direction of motion along a single straight line, then the force is always parallel, either parallel or anti-parallel to the Cartesian axis for the x-axis. We can compute the gradient operator applied to the value of x squared. This vector x squared is x squared plus y squared plus z squared. But we consider the one-dimensional case. This y squared, z squared does not appear because x is nothing but x multiplied by the E1 hat. Okay, anyway, we can take the gradient operator to x squared. X squared, this value is 2x. Y partial derivative to y squared is 2y. A z partial derivative to z squared is 2z, something like that. Therefore, the gradient operator is defined to be like that. As a result, the final result for gradient x squared, gradient x vector squared is gradient x squared y squared z squared. That is 2x e1 hat, 2y e2 hat, and 2z e3 hat. Therefore, if we can multiply 1/2 both sides, therefore the vector x in general, y e2 hat, z e3 hat is a general displacement from the equilibrium position. The gradient x squared multiplied by 1/2 is a vector x. Therefore, we can express this restoring force defined in the three-dimensional Euclidean space as a minus gradient of something that is called the potential energy. So minus gradient 1/2 kx squared is the same as the restoring force. By the way, we can take the gradient operator to any constant c. It is a zero vector. So, any force that can be expressed as a minus gradient of a potential energy should not be uniquely defined. That means it is the x dependence appears explicitly. However, any contribution that is independent of x, that is called a constant, that constant does not contribute to the force. However, because of this arbitrary constant does not contribute to the force, we can always choose the simplest case. That means the reference point x0 can be chosen to be the equilibrium position and the value of the potential energy at that reference point to be 0. Then the potential energy of the spring force is greatly simplified as a 1/2 kx squared. We still consider the same simple harmonic oscillator. Next, we consider the multiplying velocity to this expression, this equation of motion. What we find then, mass times the velocity acceleration product plus k times spring constant k times displacement multiplied by the velocity. We recall the Leibniz rule for the product. Differential of the product of A and B is AdB plus BdA. When A and B are the same, dA squared is 2AdA. if we substitute x for a, x dot for a, then we find that dx squared is a 2x dx. If I do that, it is dx dot squared is 2x dot dx dot. Therefore, we can consider this one to be 1/2 time derivative of x dot squared, 1/2 time derivative of x squared. Okay? Because of this, we can divide both sides, dx dot squared over dt, 2x dot dx dot over dt. This is a second order derivative, 2x dot x double dot. Dx squared over dt, that is a 2x dx over dt, and this is the first order time derivative of the displacement. This is x dot. All right. As a result, we find that this equation of motion, after being multiplied by the velocity and applying the Leibniz product rule for the derivative, we find that the equation of motion is equivalent to the time derivative of this sum is 0. Time derivative of sum. First of all, this term originating from this is the kinetic energy of the mass. The other term is the potential energy of the spring. Okay? And we have chosen the reference point for the potential energy to be the equilibrium position for the spring, and whose value was determined to be chosen to be 0. Finally, the sum of kinetic energy and the potential energy, its a time derivative is 0. Time derivative is 0 means it is independent of time. Independent of time. That means it is a constant of motion. It is called the total mechanical energy conservation. The total mechanical energy is the sum of the potential energy and the kinetic energy. The conservative law for the energy was not known to Isaac Newton. He did not know. The energy concept was developed by Leibniz and many others. Number 4, the equation of motion is a second order differential equation because the highest order derivative, this is x double dot, is the second order derivative of the displacement. The general solution for this equation has two undetermined parameters. They could be initial position x0 evaluated at t equals 0, and the initial velocity. When the two independent parameters are determined, classical mechanics of Newton states that x of t, the position of the particle, is completely determined forever, as long as the system is unperturbed. Once these two parameters are determined, then the solution is completely known. We call a pair of numbers, a position and velocity. This ordered pair is called phase space. Phase space. we find the phase space of this coordinate and velocity pair makes a trajectory. And you are familiar with this. Do you remember x squared plus y squared equals r squared is a circle, and x squared over a squared plus y squared over v squared equals 1 is an ellipse. And so we find the equation of motion states that the potential energy exists, and the sum of the potential energy and the kinetic energy is conserved. Therefore, this total mechanical energy is a constant, and this equation for the phase space, coordinate, and velocity satisfies the trajectory called an ellipse. That's it for today. Thank you.